Hello, everybody, and welcome to the Latin American webinar on physics, or the law physics webinar cycle that we have done many years until now. So this time is very special because we have a very interesting speaker, an interesting talk. He is Eduardo Peinado. He is from the Instituto de Física of Universidad Autónoma Nacional de México, in UNAM, in Mexico City. So first of all, Eduardo, he obtained a PhD in the Universidad Nacional Autónoma de México. After that, he have done several postdocs. One of them have been in the Instituto de Física Corpuscular in Valencia, and also in the Laboratori Nazionale di Frascati in Italy, close to Rome. So first of all, remember that you can ask questions to Eduardo during his webinar via the YouTube chat here in the live transmission. And of course, to don't make all the questions that you want. Eduardo is here he's very happy to answer the questions. And of course, the talk of today is going to be neutrino physics and dark matter stability. That is going to be given by the Professor Eduardo Peinado. Please, Eduardo, you can
Thank
start.
you very much, Roberto, and thank you to the organizers for this invitation. It's very nice to be among friends and to meet you at least in this webinar. I hope at some point we will meet again alive. So I will start sharing my screen. Okay. So this is a very generic title. Actually, I steal this from Roberto. This is a very nice picture. But my talk will be, let me see, divided in two parts. In one of them, I will talk about, let me move this. I will talk about the connection between neutrino masses and dark matter. One way is to link the stability of dark matter with the mechanisms for generating neutrino masses. And the other one is to generate neutrino masses through the Pesci-Quinn field as well. So in that way, you connect the actions with neutrino masses. And the other part of the talk, it is about one work we did recently with some colleagues at UNAM, Eric Vasquez, Luis Flores, and one of the Eric's student, Ernesto Alfonso Pita, on coherent elastic neutrino-nucleus scattering and with the SBC collaboration. Okay, so this is somehow it is related because the sevens it is important for direct matter searches, because at some point we will reach the neutrino floor, which is basically the interaction coherently of neutrinos with the nucleus in the dark matter detector. Okay, so first of all, let me see. So we have, this slide is in Spanish. So this is the poster from the PDG translated to the Spanish. So we have the standard model, which we have quarks, leptons. We have 3 generations, at least. We have the gauge bosons and the Higgs, that we found all of them. So we have the Higgs mechanisms. We break the standard model gauge group to the SU3 of color and the U1 of electric charge. Okay, so everything is good and so far. But the point here is that we don't know, or we cannot explain within the standard model why neutrino masses are massive. I mean, why neutrinos are massive particles, and why also the masses of the neutrinos are so tiny. Okay, so I will talk about this and try to connect this with other topic beyond the standard model, which is the dark matter. So the point is how to connect dark matter with neutrino masses, and also with baryon asymmetry, that we know some mechanisms to do this. Okay, but I will talk about this link in this talk. There are many ways to do this. One of these can be KEV sterile neutrino. Another way is to have the Majorana's dark matter neutrino masses at one loop or more loops with the dark matter inside the loop. And some other connections, like, for instance, the Pecha-Equidistant symmetry and the axiom, okay? So we know that neutrinos are massive particles because we observe the oscillations, I mean, from the sun, from reactors, in the atmosphere, from atmospheric neutrinos. And basically, it is because neutrinos are massive and the masses are different. If all the masses of the neutrinos were the same, this delta m squared would be 0, and then this probability of oscillation will be 0. And the other one is because they mix in the sense that, like in quantum mechanics, the weak eigenstates that you produce or you detect are linear combinations of the massive eigenstates, okay? So what do we know about neutrinos, or what are the interrogants we have to, or we need, or we want to find? Is what is the hierarchy of the neutrino masses? We know that there are 3 masses. Two of them are very close, M1 and M2, and the other one is different. I mean, the difference between the M3 and M2, or M3 and M1, is bigger than the difference between the 2 and M1 and M2. It is like 30 times bigger, okay? So, but the question is, the sign of this delta M 3.2 or 3.1, is it positive or negative? So if M3 is bigger, that is the normal hierarchy, where you have one mass that is bigger than the other 2, like in the charged fermions or quarks and leptons, or it is inverted. That means that 2 of them are bigger than the other mass, okay? And the other question is if neutrinos are Dirac or Majorana particles. That means that if neutrinos are Majorana particles, that means that they are their ordinary particles, and then you can have, for instance, this process that is the neutrinoless double beta decay, that is double beta decay without neutrinos in the final state. Okay, so this process, in the case where neutrinos are Majorana particles, is non-zero in most of the cases. Okay, so there is in the parameter space chances for this process to be also 0, but it is unlikely, and hopefully it's not the case. Okay, so what do we know? For neutrino masses, we have some bounds from the tritium beta decay. You have the effective mass for the electron neutrino. We know from 2019, the last the data from Catherine, it is smaller than 1.1 electron volt, which is 6 orders of magnitudes below the electron mass. Okay, so the smallest or the lightest charged fermion is 6 orders of magnitude heavier than neutrino masses. Okay. From cosmology, we also have some bounds, which are even smaller than the direct bound from Catherine, which is, it depends on what do you choose or what you combine, but let's take this number, smaller than 0.12, 0.15 electron volt, which is even smaller than the effective bound from Catherine, okay? So from the oscillation parameters, so for 3 neutrinos, you have 3 mixing angles, okay? And what we have now is 2 of them are big. I mean, the solar and the atmospheric. This is close to maximal, this is big. And one small, that is the reactor mixing angle, which is small, but is of the order of the biggest in the quark mixing matrix, namely the Cabibbo angle. And we have, for 3 neutrino mass eigenstates states two square mass differences. Okay, so those are the oscillation parameters that we can extract from oscillation experiments, and the Dirac CP violation. Okay, if neutrinos are Majorana particles, then we also have extra phases that can have an effect in for instance, in the neutrino double beta decay. Okay, so there are three ways to test these masses of the neutrinos. One is the direct tritium beta decay. This is the effective mass parameter, where you have the masses of the neutrinos and also the mixing parameters. The double beta decay, where you have the masses of the neutrino, the mixing parameters, oscillation parameters, I mean mixing angles, and also the Majorana phases and the Dirac CP phase. And from cosmology, you have directly the mass of the three mass eigenstates. Okay, so this you will have it only if neutrinos are Majorana particles. Okay, and this is very important because if we observe this process, that will means that neutrinos are Majorana particles according to the black box theorem by Schechter and Baye. Okay, I will come back to this later. So we can combine the two of the observables, for instance, the lightest neutrino mass, and we can plot versus the sum of the neutrino masses for inverted ordering or direct ordering. So basically you have the two square mass differences coming from the oscillation parameters of oscillation observables. So you can plot, you can put this sum as function of the lightest neutrino mass for normal ordering, or the inverse ordering, which is the M3, the lightest. Okay, so when you plot this, then you have the exclusion coming from cosmology, and then these bounds are going down. Okay, in time. So they are excluding or setting a bound for neutrino masses bigger than, it depends on which hierarchy you have, bigger than certain number. Okay, and you can also combine, for instance, in the case of Majorana neutrinos, either the sum of the masses or the light of neutrino masses. Okay, so this is, in this axis you have the neutrino double beta decay effective mass parameter. In this in the X you have the sum of the neutrino masses. In this case you can also use the lightest, like in this plot. And the point in here is that the experimental bounds, now I think we are more or less here. This is from 2014, so nowadays is more restrictive. These experiments with time are going down, and at some point we expect that the inverse hierarchy will be surpassed by the experimental bounds, hopefully. And if, of course, if neutrinos are in the inverse ordering, you expect to have a signal, because this is bounded from below. In the contrary, if neutrinos are in the case of a normal hierarchy, where M1 is the lightest neutrino, then it is possible to have cancellation by means of the Majorana phases. Okay, so even though neutrinos could be Majorana in nature, exists the possibility, it is possible to have a very small or negligible effective Majorana neutrino double beta decay. So that would be very sad if that is the case, but nature is what it is. So let's see what the experiments tell us. Okay, so we can combine the observations in one side and the other and try to say something. Okay, so what could happen? That it will be very interesting, for instance, if Catherine sees something, because if you see here, this is, if you see here, Catherine, the sensitivity will be like 0.6 electron volts, which is far from the cosmology. So if Catherine sees something and neutrino-nucleus double beta decay is seeing nothing here, then it will be very interesting because there would be a tension there that could means that neutrinos are Dirac particles, for instance. Okay, so let's move. So this is the plot of last year from CMS. There's another plot from Atlas, very similar, where you have the couplings of the Higgs with the particles versus the mass of the particles. Okay, basically you have a straight line. And the point is that lighter the mass, you are on the left, okay? So this is very outstanding, the errors you have here from the experiments. So everything is basically consistent with the standard model, right? But the point here is that the couplings, lighter the particles, lighter the coupling. So neutrinos are somewhere on the floor, okay? Or underground, depending on the scale. So something like this. So actually this is from Atlas, but this is an old plot. If you see the errors in here, were not as now for the muon, for instance, that now we have a measurement. Okay, so how can we explain a Yukawa coupling with the Higgs of the order of 10 to minus 12, 10 to minus 13? Either we put it by hand, if neutrinos are Dirac particles, or we find the mechanisms, okay? If neutrinos are Majorana particles, by means of the dimension 5 Weinberg operator, which is non-renormalizable, so you have a suppression, one scale suppression. If the scale is high, then the neutrinos are light, okay? So then you can have Yukawa couplings of order 1 for the neutrinos if you have a scale that is suppressing neutrino masses, in the case of Majorana. And there are also some low scale seasons, so you have extra suppressions, okay? But you can also play this trick in the case of Dirac neutrinos by modifying, of course, or playing with some models. Okay, but in the case of Majorana, is somehow easy and natural to explain neutrino masses that are smaller. Okay, so the question is Dirac or Majorana? Till now, it can be either Dirac or Majorana. There's no exclusion. In one case, you have one observable that you can try to look at, and the experimentalists are making efforts to measure this because, as I mentioned before, if this process is observed, that means that neutrinos are Majorana particles. Otherwise, if Dirac and you have a small effective coupling in such a way that you explain this effective Yukawa coupling of 10 to the minus 12, 10 to the minus 13 effectively, like increasing your model with particles and symmetries in such a way that you suppress the direct Yukawa coupling and you generate it effectively. Okay, but the question is there. So this is the way you can construct within the standard model only using only standard model fields, namely leptons and Higgses. This is the operator that breaks lepton number into units. Is let's say the lowest dimension within the standard model that breaks lepton number, and it's dimension 5. So you have a scale here. That means that if this scale is big enough, then you can explain why the neutrino masses are so tiny. So, and the implication, if this happens, is the black box theorem tells you that if you observe this process, then that implies Majorana nature for neutrino. Okay. As I mentioned before, it is also possible that even if neutrinos are Majorana particles, this process can be very, very small, the effective mass parameter. That means that the experimentalists will have a hard time trying to observe this, and maybe it cannot be observable. And then you have to look either in extensions of the standard model in colliders or other processes, like, for instance, in atomic muonic atoms, like you observe in the final state, for instance, a positron, then you have a delta L equal to, you start with a muon and you end up with a positron, okay? But that is also a very rare process, so it is hard. But you have some extensions of the standard model, like, for instance, left-right symmetry, where you have extra gauge bosons. Then you can also have contributions to this kind of process that, for instance, you can look at colliders, like proton-proton collision, and then you have delta L equal to in the final state, okay? So the CISO, it is very, as I tell you already, if neutrinos are Majorana, then to UV complete this effector operator, the Weinberg operator, is kind of easy and well known, and there are several options, okay? So one thing is the left-handed field of under SU2, the left SU2 is a doublet. The Higgs is also a doublet. So you have doublet with doublet, you have either a singlet or triplet. So what can we do with this? We can include to the standard model the right-handed field, the neutrino right-handed field, which is a singlet of the standard model. It is allowed by the symmetry. You can also add, if you have doublet with doublet, scalar triplet, which is the type 2 CISO. You can also have a doublet with doublet, and you add a fermion triplet under SU2, which is the type 3 CISO. And the thing here is that if you add, for instance, the right-handed fields, the Majorana mass for the right-handed field, that means the n bar Cn or Nn coupling in the Lagrangian is allowed by the symmetries of the standard model, which is trivial because this is a singlet, right? So the dimension 5 Weinberg operator, effectively, you have here, you can put the bubble, you have the dimension 5, 2 Higgses. Sorry. You have the 2 Higgses here, the 2 leptons here, and then you integrate out this heavy state. If the Majorana mass for this N field is big, then you integrate out. You also have this topology for the type 2 CISO, which basically the 2 Higgses induce the bevel of the triplet. And then you have the dimension 5 Weinberg operator, or also the neutral part here of the sigma, which you have, it is a triplet. It also contains electric zero electric charge field there, like basically like the N, and then you integrate out this heavy field. Okay. So the full mass matrix for the Majorana particles, the left part and the right part, is as follows. This is coming from the type 2 CISO. This is the Dirac, the Yukawa coupling for Dirac. I mean, the coupling of the left field, the right field, and the Higgs. And this is coming either from type 1 or type 3, from the Majorana mass for the N or the sigma 0 in here. Okay. So basically, that is the CISO. This is heavy in comparison with this, and this is very small. Okay. There are other ways, the other CISO, low energy CISO, and for that you need extra fields. For instance, you add an extra fermion which transform just opposite to the N field, to the right-handed field, in such a way that you can couple directly these two fields in the Lagrangian, N with S. Okay, so they form like a Dirac pair of heavy pairs. Okay, so the mass matrix is like this. You have the left-handed field, the N and the S, and then you have this, the Dirac pair like couples this with of N with S. This is the Yukawa coupling, and then you add a small term that breaks this lepton number, okay? So the diagram is, in this way, neutrino masses are 0 if this mu is 0, and you recover lepton number as a symmetry, okay? In the diagram, the topology of the dimension, the effective dimension 5, this is not dimension 5, Weinberg operator is this. So this is the Higgs field, then the left-handed field, the Higgs field, and then you have this mass insertion, which is the mass coming from the Dirac pair between the S and the N, and this is the mu term. Okay. You have other options like the C or C-Babu model, where you include electric charge scalar fields that couples the left-handed fields with the charge fermions, for instance, in this case. And then you plug here one Higgs and another Higgs. So this is the dimension 5 Weinberg operator generated at one loop or two loops in the C-Babu model. But there is another option that is very interesting, which is you include the dark matter stuff, the dark matter sector, inside the loop in such a way that you connect the neutrino mass generation with the dark matter sector. So you link both sectors, okay? And then you have the dimension 5 Weinberg operator. So you have an extra suppression coming from the loop. And this is the Scottogenic model. And of course, this is the simplest case, but you can imagine that you can have 2 loops, 3 loops, and so on and so forth, okay? And the nice thing is that in this case, which the eta field in here, that I call it eta, is an SU2 doublet. It's like the Higgs field, but is stable, okay? So, but the point is that once you have the electroweak symmetry breaking, you have what we call Higgs portal. That means that you have the Higgs, if you put above here, this is the quartic coupling, then you have the Higgs with 2 dark matter states. So the Higgs with 2 dark matter. And then it is important because it can help you to have the correct relic density. It can also help to have direct detection of dark matter. For instance, you have the dark matter, they exchange one Higgs fields, and the Higgs can couple to the nucleus, okay? So it is very important, it is very nice. Okay, so this is some ways to generate the dimension 5 Weinberg operator are 1 or 2 loops, okay? So what I want to talk about is the dark matter stability. So that means that if we have these kind of particles, we want them to be stable or at least very, very long-lived. So the easiest way is to have a symmetry that protects the dark sector to be stable. So that means that the lightest particle in the dark sector is stable, okay? So, and to have something stable, you need a symmetry, either accidental or an exact symmetry, okay? Or very long-lived, but I will focus on, at least in the beginning, in this part of the talk, to the stable by asymmetry, okay? And I will focus only in U1 symmetry, which is very, very easy. So you have the U1 symmetry parameterized by a theta. And the U1 symmetry, you can break it. And the U1 symmetry contains a lot of subgroups, basically the cyclic groups, set n. The smallest is the set 2, which is what we use in the Scottogenic model, for instance, in the previous one that I use here. If you charge this eta field and the n field with a set 2, that means that either the lightest particle in the eta field or the lightest of the n is stable by means of this set 2. But this set 2 can be a subgroup of one U1 symmetry, okay? So it can be set 2, it can be set 3, it can be set n, okay? A cyclic group. And the question is, can we use this by having one U1 symmetry like the U1 of QED? This can be, of course, a gauge like QED, or it can be global symmetry. It doesn't matter for this purpose. So we can ask, can we use one extension of the standard model with one U symmetry, gauge or global, that gives you, by the spontaneous symmetry breaking, a subgroup of this U1 that renders stable the standard matter, the dark matter? And of course, the answer is yes. So for instance, if you want to explain why the case of Dirac, I explained already Majorana, but you can also explain a Dirac mass, which is small, effectively generating this 10 to minus 12 coupling of the left-handed field, the right-handed field, and the Higgs at higher dimension. Like for instance, in this case, this is dimension 5, and it is generated at 2 loops. It is very nice because you have 2 loop suppression and 1 extra scale suppression because it's dimension 5. Okay, so basically this operator is L, N, H, and sigma. So you need 1 over lambda, like in the dimension 5 Weinberg operator. Okay, so but to have this double suppression and Dirac neutrinos, you need symmetries, right? As I told you before, there are no symmetries in the standard model that forbids Majorana masses for these right-handed fields because they are singlets of the standard model. So there's no way to forbid that. So you need a symmetry that gives you the Majorana nature of neutrinos, which is basically a set 3. A set 2 is not possible because a bilinear term with n, if they transform as -1, it is invariant under set 2, okay? So you need a set 3 symmetry at least, or lepton number. You want lepton number as the symmetry, but the smallest one is set 3, okay? Where omega cube is 1. And to forbid, of course, the direct coupling between the H, L, and N, you also need another symmetry. Otherwise, it is not forbidden by the standard model group. And you also need a sigma field that breaks the symmetry you are imposing to forbid the direct term, the Yukawa direct term, L, H, and N. So you need one to forbid the direct coupling, one to forbid Majorana masses, and the other one is to get no 1 loop, but 2 loop, an extra suppression. Okay, so you need 3 symmetries to get this. In this case, I didn't mention that, but once you have the 2 loop, this set 3 in dark matter is not broken by any field. All these scalar fields that are quite bad, like sigma and H, are not charged under the same symmetry. So that means that you have a dark matter candidate inside the loop by means of this set 3 symmetry. Okay. So, but the question is, can we have something like this, but without using all this budget of symmetries? So let's move to the U1B minus L that is already in the standard model. So this is a U1, and of course it depends how do you break the symmetry. If you can have a residual symmetry that can give you the stability of the dark matter, and also it can tell you if neutrinos are Majorana or Dirac. Okay, so if this set M, the M is even or odd, will tell you if neutrinos are Dirac or Majorana. If it is odd, then it is possible for the neutrinos to be Majorana, like in the case of set 2. Of course, it depends if neutrinos transform as, let's say that this M is 2n. If the neutrinos transform as, or leptons transform as n, then the bilinear is invariant under this set M symmetry. Okay, so that is the only option for neutrinos to be Majorana if you use this B minus L in this breaking. Okay, but if the M is odd, then neutrinos, of course, should be Dirac particles. Okay. And the other thing is you want to have this U1 B minus L anomaly free. That means that you can gauge afterwards this symmetry. But let's focus on the anomaly free solution with 3 right-handed neutrinos. You have the canonical, which is okay, and you can have this direct Yukawa coupling of the left-handed fields, the right-handed fields, and the Higgs. Or you can use this other solution, which of course forbids this term, because this is -1, this is 0, and then this is either -4 or 5. So there's no match there. That means that you need to generate this Yukawa term at higher dimension, which is good if you want to explain why this Yukawa in here effectively is small. Okay, so in here you already have the answer of how to have Dirac neutrinos or Majorana neutrinos. Okay, and we will use this solution from now. Okay, this is an example of this U1 B minus L, and the goal is to have also dark matter stability. Okay, so you will generate this effectively, and what we want is to have something like before, 1 loop or 2 loops, with some particles inside the loop there, and can be stable by means of the residual symmetry. Okay, so this residual symmetry will tell you if neutrinos are Dirac or Majorana. I'm trying to focus on Dirac particles. You can play the same thing with Majorana neutrinos in this reference. You can find the way. It is basically, you can generate this photogenic model effectively. Okay, starting from U1 B minus L. So this is an example where you have the B minus L, which is broken to set M. In this case, of course, you can have also Majorana neutrinos, but we choose this to be even because it is important for dark matter stability. Okay, the n should be bigger than 2, because if this is set 2, is of course neutrinos are Majorana, and then there is no stability for dark matter. But if n is bigger than 2, that means that you start with set 4. This model is with set 6, but it's just an example. Basically, this is those are the charges under U1 B minus L. Once you break the symmetry, then those are the charges under the set 6 symmetry. Okay, so the fields inside the loop are odd under this symmetry. Okay, and this is the reason why we want to have these even numbers here. Okay, because in set 2M, if one field transforms as odd, the conjugate will also transform as an odd field. Okay, that means that if you have a dark matter candidate or some particles inside the loop that are odd under the set M symmetry, the dark matter is automatically stable. Okay, there's no way, because all the particles outside are even. Okay, so that is the way how, or the recipe that how can you get dark matter stability coming from this U1 B minus L in this case, and also having Dirac neutrinos using only U1 B minus L. So all the 3 symmetries we used before are reduced to this B minus L. Okay. You can also construct a model with several loops. That means extra suppression for the Yukawa effective coupling. And in this case, if the standard model leptons are even powers of the symmetry, the dark matter can be either fermion or scalar, transforming as odd. And those are automatically stable, like in the example before. But there's another option for the stability. If the standard model leptons are odd powers of this residual symmetry, the scalar dark matter transforming as odd automatically it is stable, right? Because you will need at least an even number of fermions in the final state, and of course that is even. Or fermionic dark matter transforming as even, it is also automatically stable because you will need an odd number of fields, of fermion fields in the final state. So that is the recipe if you want to construct a model for Dirac neutrinos or Majorana neutrinos, doesn't matter, with dark matter stability coming only from U1 B minus L. Okay, if this is B minus L. Of course, you can change this B minus L and use only L and call it X, but the recipe is exactly the same. Okay. And now I will move to another U1 sector, which is the Peccei-Quinn. So you have two options, basically, the KSB set or the DFS set, where you have, in this case, exotic quarks, or in this case, the standard model is charged under the Peccei-Quinn. Okay. If we concentrate on this model, on this kind of model where the standard model are charged under Peccei-Quinn, so you need two Higgses. You have two Higgses charged under the Peccei-Quinn, and you have two options for coupling the Higgs sector, the two Higgses, with the Peccei-Quinn field. Either is a trilinear or quartic coupling. Okay. If we take the trilinear option, that means that you can assign, for instance, Peccei-Quinn charge to the HD as 1, and the sigma field to be 2. Or you can redefine your fields and charge this under the Peccei-Quinn 2, and 4. Okay, that is why we have the conjugate. So basically, this is the model without mentioning the right-handed fields. If all the standard model fields transform as 1 under the Peccei-Quinn, H up and H down are 2 under the Peccei-Quinn, and sigma is 4, as I mentioned before, that means you have all the Yukawa couplings, you have everything, and you have this trilinear term. Okay. If that is the case, we have demonstrated that in this case, you cannot generate dimension 5 Weinberg operator, nor higher dimension operators with these fields, sigma and H up and H down. That breaks lepton number into units. Okay, so you cannot generate the dimension 5 nor higher dimension versions of this. I mean, LL in some fields that break lepton standard model gauge group or the Peccei-Quinn. And you can go and see how this dimension 5 options you have within the standard model gauge group, and they transform as -2, +2, or +6 under Peccei-Quinn. So there are no way you can combine the scalar fields that match these numbers. So all of them transform either as 0 under Peccei-Quinn or 4n. So there is no way that you plug all these operators to this in order to generate a higher dimension. So impossible to have Weinberg operator at any order in perturbation theory. So this means that neutrinos are Dirac particles, okay? So you can say, okay, maybe we can generate and explain why this effective Yukawa coupling is so small if we generate the Dirac mass at dimension 5. Of course, if right-handed neutrino transform as 1 also, then you basically build the dimension 4 operator for Dirac neutrinos, and that's it. But if you want to explain why neutrinos are tiny, then you have to generate neutrino masses with the Pesci-Quinn field. Okay, so I will not lose more time because I want to go to the other topic, but basically you can have a UV completion with the type 1 CISO. If you can also have, if you go to this paper by De La Vega, Nat, and myself, you have other topologies, but this is the easiest way to build the effective dimension 5 operator. And of course, you can see from here that the neutrino mass is proportional to the Pesci-Quinn scale. So bigger the Pesci-Quinn scale, bigger the neutrino masses. So you can use that. Okay, this is compatible with GATS. The main thing here is that bigger the scale, F, bigger the neutrino mass. So if using only the bounds from Catherine without using the cosmology, then that constraint already put some constraints on the parameter space in here of mass of the axion or coupling of gammas with axions within this model, of course. So for using the UV completion, I mean you have the suppression of sigma over m using Planck scale for this m. Then you have this bound. Everything below this pink band is excluded within this model for this Yukawa couplings, 10 to the minus 4. But if you use GATT scale, that means that the bounds are even bigger. I mean, more constrained the model is. Okay, lowering the UV scale, that means that you lower also the FA. Okay, so I will move to the other topic now, that is coherent elastic neutrino-nucleus scattering, which is very interesting because you can have bounds for the muon magnetic moment. You can have constraints for non-standard neutrino interactions, or NSI, or you can also have some proofs of precision within the standard model. Okay, as I will explain later. So basically, what you have is very low energy neutrinos interacting with nucleus, and below these energies, neutrinos below 50 MeVs, then they interact coherently. Okay, so this was first study in the 74, but this was measured in 2017, so a few years ago. So you can have coherent in accelerated neutrinos, reactor neutrinos, also from solar neutrinos. You have, for the experiment on direct matter detections, the neutrino floor, also part of the supernova diffusion neutrinos, or some also part of the atmospheric neutrinos. Okay, so if you look at this is basically the cross section for the coherent, which is for energies of the neutrino below 100 MeVs, is the biggest of them. And the problem was why this it took all this year to be measured or detected. It is because the threshold you need for these detectors are very, very small. So, or the order of 10 kilo electron volts, right? And also, of course, the background. So this is the bigger cross section, but you need detectors able to detect those neutrinos. So very low threshold detectors. Okay. So those are the cross section depending on the element you use. More neutrons you have, bigger the cross section is. So you can pick up one of them, okay, and build your detector. So basically, the cross section is a good approximation for small energies. Only the vector current is contributing. I mean, the axial part is negligible or zero in some cases. It depends on the spin of your nuclei. And basically, this is the cross section. It depends on the energy of the neutrino, the recoil, etc., and the mass of the target, of course. And then it is proportional to the number of neutrons in your target squared. Okay, so this is the F, the form factors for N and protons inside the nucleus, depending on the energy momentum transfer. Okay, the good point in here, I will talk about the reactor neutrino part, is that for reactor neutrinos, you are in this area where the form factors are basically equal and very close to 1. If you use accelerated neutrinos, then you move this line to the right, and then you have some you depart from 1, and you depart from them to be equal as well, which is good for having some insight in the nuclear form factors. There are papers on that. And for the reactor neutrinos, what is good is that you don't have access to that, but at least you don't have errors coming from that as well, or the errors are negligible. Okay. So cross-section 4/7s are also sensitive to neutrino non-standard interactions. So you modify basically your cross-section with this epsilon, which are the NSI effective parameters. Okay. So are very interesting and very helpful to constrain physics beyond standard model as well. So up to now, we have only data coming from, observation of this process from the coherent collaboration in 2 different nuclei. And what they have is basically they produce neutrinos from muon neutrinos, basically a monochromatic beam of muon neutrinos, and antineutrinos of muon, and electron neutrinos. Okay, so this is different of what you have in a reactor where you have only antineutrino, electron antineutrino. So they are kind of complementary. There is a complementarity between these 2 different experiments. Okay, so basically this is what they have in the spallation neutron source. This is the flux of the antineutrino of the muon that stop here, because of course those are the energy of these 2 neutrino and antineutrino are bounded by the mass of the muon, and this is the monochromatic coming from this muon neutrino. Okay, so far they have a detection of 134 events in 300 days, and of course they have errors in here, but I'm not displaying them. They detect in 24 kilograms of argon 159 events in 240 days. Of course, they are taking more data, and they will continue doing this with other elements. And the point is that if you use reactor, the flux is way above what you can have in the spallation neutron source. But the problem is that the energies of those neutrinos are lower than what you have in these accelerated neutrinos. And of course, the threshold you need in your detector is lower. Lower the mass, lower the energy of the neutrino for one target, lower the recoil. So lower the threshold you need to detect those neutrinos. Okay, so that is the issue. There are many proposals. So if you go to this reference by my friends Diego Aristizabal, Valentina de Romeri, Luis Flores, and Dimitris Papoulias. You will see all the list of the proposal we have now for detecting sevens at the reactors. Okay, so I will talk about this one here. That we discussed two possibilities. One is a small reactor at ININ, and the other one is a power reactor at Laguna Verde. You see here the power. One is very small, but you can be very near the detector, and the other one is powerful, but you need to be far from the detector. Okay. So, as I mentioned before, basically this is the sum of this power here and normalized, because it is different for a small reactor than for a big reactor. So the two cases we study is placing this detector, which is basically very similar to the Pico detector. It's a bubble chamber at 3 meters from the reactor. And then, of course, you have shieldings, water, lead, etc., because you need to get rid of as many of the background as possible. And also we placed, this is a 10 kilogram detector, so small detector, or a 10 kilogram detector at 30 meters from the power reactor. Okay, so what else I have to mention here is that this is already under construction. The 10 kilograms detector is already under construction by the SBC collaboration. If you want more details, you can go to this reference in here, or the organizer can invite either Eric Vasquez-Jauregui, that I think he already gave a talk in this seminar about the PICO collaboration, PICO experiment, which is similar to this, but for dark matter direct searches, or Eric Dahl, which is the spokesperson of the SBC. Okay, any of the two Eric you can invite, or both if you want. Okay, so this is basically what we use. Ernesto Alfonso Pita, a student, to study the background. This is the modeling we have. So you have in this inside, you have the 10 kilograms argon. Then you have some liquid to keep the thermal bath, and also to keep the pressure or calibrate. You have to have this liquid argon at between 90 and 130 Kelvin, and at a pressure of 2 atmospheres, more or less. So the detector is pretty similar what we already have in the PICO detector. So 100 electron volt threshold. So they can reach a 0.1 keV threshold for the detector. That means that you will be able to get more or less from this point. So the minimum energy you have is 1.56 MeV, around here. So you get all the neutrinos from here to these energies. So bigger the threshold, smaller the threshold you have, bigger the flux you access to. Okay, so this is very important. If you see here, in the cesium, in these two detectors, they catch 134 events and 159 events. So since the reactor, the flux in the reactors is way above what you have in the spallation neutron stars, of course, you can have, with a 10 kilogram detector at 3 meters from the 1 megawatt thermal reactor, 8 neutrinos, 8 event of neutrinos per day. That means 2,900 neutrinos in 1 year. Or if you, of course, build a 10 kilogram detector and place it at 30 meters from a 2,000 megawatts thermal power reactor, then you can have of the order of 1,500 neutrinos per day, or 570 10 to the 3 neutrinos in 1 year. Of course, you have the background, but this is more or less under control. You have background coming from cosmogenic neutrons, or also neutrons produced inside the roof, okay, or the water that you are shielding with, okay. So what we can do with these two detector or place at different distance from the reactors, it is that you can study, for instance, sevens and for any side. For instance, this is the case where you have a Z prime coming from a U1B minus L. This is the effective Lagrangian you obtain with this Z prime, and you can set bounds with these two possibilities we have for placing this detector. So basically, for small masses of this Z prime gauge boson, this will be very good, or even for this gap we have in the accelerators, okay? But this is not the only thing you can do. Of course, you can this is the one of the structure of this NSI. You can also study some other NSI, other structures of neutrinos with nuclei. You can also, if there is nothing but the standard model, you can also try to measure the theta Weinberg. That if it depends on which of your detectors you use, and also how you control the neutrino flux, because you have basically what gives you this error. The biggest thing is the error in the neutrino flux. Then you can be more or less in the same order of the errors we have from atomic parity violation for low energy measurements for theta Weinberg, okay? And also you can constrain or see what are the constraints for the magnetic moment of the neutrino. Those are coming from already the coherent collaboration, the two detectors. And also depending on which setup you use, this is Laguna Verde, this is ININ, the small power, the small research reactor of 1 megawatt, or the Laguna Verde, depending on, of course, this is depending on what errors do we have for the neutrino flux. And this is basically the bounds you have at 90% confidence level is 5.4 10 to minus 11 of the Bohr, which is basically in the same order of what we already have, the best limits we have from GEMMA and Borexino collaborations, okay? So now I conclude. So in the first part, we discuss the link between some scenarios of dark matter with neutrino physics and the nature of neutrinos with dark matter stability, and to explain also the smallness of neutrino masses for the Dirac in this case. Also neutrino axion complementarity if you connect the Pesce-Quinn with the neutrino masses. And also sevens can prove physics beyond the standard model, like this case of, what is this? This sevens, for instance, this is a gauge U1B minus L, but you can also have, as far as, in this case, as far as the electron flavor is charged and there's the symmetry, the bounds are similar. Of course, these are using reactor neutrinos for coherent collaboration that they have muon, anti-muon, and electron. You can also have, if you have muon and tau, it is possible to have some bounds as well. And 17 reactor neutrinos with low threshold, very low threshold, 0.1 keV, are very promising and currently under construction, in this case for the SVC collaboration. And it can be placed either in a 2 gigawatts thermal reactor, power reactor, or a research reactor of 1 megawatt. maybe in Mexico. So stay tuned for more results coming from this part of sevens. Okay. So thank you very much. I don't know if I.
Thank you, Eduardo, for the nice webinar. It was very interesting with many topics. So let's start with first of all, to remind to the viewers that you are now following the transmission in our YouTube channel. So if you like, you can subscribe to the channel to be updated with every activity that we are doing here in lawphysics. Of course, also you're invited to follow us in the different social networks that we have. So in order just to keep in touch always we have very interesting webinars like the one that we have today. So let's start with some questions for Eduardo. Let's start with one from YouTube. Remember to write a question in YouTube. We're gonna be reading and giving to Eduardo. But there is one from Cristian Angelo Calderon Cordova. He's asking, what is the kind of dark matter in the residual symmetry Zn? I mean, it could be WIMPs, action, etc. Or why is it that type? So he's asking about the.
Yes, let me go there. You mean in the U1B minus L, right?
Yeah, and the one that you have.
Yeah, in the residual, yes, not in the pressure pin. It can be either. It can be either a fermion or scalar particle. So anything inside the loop. So something outside the standard model, of course. No? In this case, you have extra fermions and extra scalars that are charged under, of course, the U1B minus L in this case. And they are charged, of course, under the residual symmetry. The end-like, I mean, it's like they are like the right-handed neutrinos. Those are fermion fields. Yes. And the dark matter can be either of them. Of course, in the scalar, the scalar dark matter is easier to fulfill the requirements of relic density.
Okay, there is, I don't know if there are questions from here from the audience. Maybe
I have a question.
Yes, please.
Can you guys hear me?
Yes.
Thanks, Roberto, for the super nice talk. Just out of curiosity, at the very end you mentioned about the SBC collaboration. What's the time scale for the detector?
Very good question. That is a question for the experimentalists, but since this is already under construction, but of course we are in the very hard times of the pandemic, I think maybe in 2 years the detector could be, finished. I don't know. I mean, I know that this already under construction. I think the money is there to build the detector, and of course these people already build the PICO detector, so they know what they are doing. But I don't know in these times. But I think 2 years could be. I don't know.
So maybe in 3 or 4 you can have physics results, right?
Well, I have to say that in this, I said 1 year, right? But this 1 year in the case of in the research reactor at ININ, this one, the time of the detector, sometimes it is off and sometimes it is on, which is also, I didn't mention that, but it is also important for us because in that way you can measure the background coming from the cosmogenic neutrons. So when you start operating, maybe 1 year of detection could be 1.5 years or 2 years, or depending on the people from ININ in this case, right?
Okay, thanks.
So is there another question? We have more questions from YouTube. First of all, we have a hello from Carlos Alvarado. He's saying hello to Eduardo.
Hola, Carlos.
Also, there is a question from Gerardo Morales Navarrete that he's asking if it is possible that there is a combination between Majorana and Dirac particles. It's a very question.
Well, it's a very good question. I mean, first of all, if you have Majorana particles, I mean, the seesaw, normal seesaw, you can demonstrate that what you have at the end of the day is that particles are fulfill the Majorana condition, that you have a neutrino, which is the complex conjugate. But there are some particular cases that you have, for instance, very, very small numbers that violates lepton number, which means basically, let me go to the mass here. And this particular case where this dominates against this is what we call quasi-Dirac particles, or pseudo-Dirac, because they behave like Dirac particles, right? But basically, you can describe also a Dirac particle as two Majorana particles with different or opposite CP behavior, right? Or in the mass matrix, one with positive mass and one with negative mass. But in that case, if this is small and this, let's take what this does not exist, but when the mass of this particle is small, then you have basically quasi-Dirac, something that is very similar to Dirac.
Okay, let me check here in YouTube. No, in YouTube there's people writing question, I guess. So it seems that Joel wants to.
Yes.
Ask the question.
I thought that you were gonna go first, so but I'll do the question first. When you presented your scotogenic models, you're trying to solve neutrino masses and dark matter at the same time using combinations of symmetries and new particles. The question then is, can you also solve G-2, the muon G-2 with these models?
I don't think so. You mean by having one pseudoscalar which is light and blah blah blah, in that way, or using the gauge boson itself? So you have two options, right? I mean, the muon is charged, and there is of course this U1b minus. Let me go there.
Yeah, that's what I was thinking.
Yeah, with a set prime, not with the extra scalars.
Well, okay, so since they were charged, you could go, they could couple with the extra scalars, right? And then you can make a
that is
right.
Let me see if I have I think we didn't, because in this plot you can also put the G-2, right? This is the M set versus G. This will give you a contribution to the G-2 of the muon. Let me see if I have another plot, because this was part of another work, which is this basically. Let me see if I find it here. I think I have it in the backup slides. This one, yes. This was previous to the SBC. I mean, the SBC study, but this is already with the new data of Coherent. Okay. So this band is coherent, one of the coherent, and this is the other one. This is the G-2. In the case, of course, this is B-2 minus 1 lepton number, but it doesn't matter. As far as this thing couples to the muon flavor, you have explanation for G-2. That means that this explanation for G-2 is already excluded by coherent data. Coherent data that is already there. I mean, coherent collaboration is what I meant.
Right.
So this G-2 coming from Z prime is already out. Yeah.
And what about the possibility of coupling with scalars and fermions?
If I remember correctly, you need a very light pseudoscalar to reproduce to give you this G-2, right?
Right. So I'm just making the analogy in supersymmetry that your leptons must not be too heavy, right?
But if this pseudoscalar is in the dark sector, then It is not this direct coupling of the muon with the pseudo-scalar and you close the loop. If that is the dark matter, you need to close with the dark matter thing, right? So I think it is not possible because otherwise you will have contributions also to mu 3 gamma, etc. I mean, within the concept of dark matter. So I think it's very unlikely to explain.
Great, thank you.
Okay, we have another question from the YouTube channel, from the chat. Alexander Cáceres, he's asking, sorry, I lost the part of the indirect detection of action Pechiquin in the neutrino experiment, and he asking, could you explain more about that UV complementarity?
In
the indirect detection of action.
This one.
Yeah, if you can explain more about.
Yes, basically, I mean, this is general, right? The model we are discussing here are those bands, okay? Since basically the Dirac mass is proportional to Fa and inversely proportional to the UV completion, I mean the UV scale, which is basically the mass of this pair here. This is the type 1, okay? And that means that basically, depending on which scale you choose, this M Planck, and setting the mass of the neutrino here. Of course, this is very simplified. You say, okay, I want this to be 1.1 electron volt. Of course, you need to translate this to the electron neutrino effective mass parameter, but forget about that. Saying that this is 1.1 electron volt, which is the bound from Catherine. This gives you this line. That means that all the masses above 1.1 electron volt, setting the product of the two couplings, these two couplings, this and this, to be 10 to minus 4, you can have one that is. The other thing is that if you make the UV completion in the SO10, for instance, that you can do it. You can go to the paper and we more or less explain how to do it. One of the couplings is of the order of the top Yukawa coupling, which is a 1. Okay, that means that one of these Yukawas is of order 1 and the other one is small. So one of them already 10 to minus 4, or 10 to minus 6, which is the electron Yukawa coupling. That means that for the UV at a Planck mass scale, you are excluding all the FA to be smaller than 10 to the 13, or in this case, 10 to the 11. If you lower, this is the biggest scale you can have, right? Planck scale. If you lower and you say, okay, I want my model to be in the SO10, then you use GAT scale, or a bit above GAT scale. It depends on your model and the proton decay, etc. In that case, in saying that, okay, now I set 10 to minus 5, 10 to minus 4, and 10 to minus 6. That means that if this is 10 to minus 5 already, this Yukawa coupling is very small, you pay the price. This Catherine bound is excluding scales for the Pechiquin of the order 10 to the 9, 10 to the 10, between 10 to the 9, 10 to the 10. So, and this is using Catherine. If you use cosmology, this bound will go up. So that means that this model is really, really constrained from the masses of the neutrino already. Of course, I mentioned that we did two different UV completions. One is, this is like the topology of the type 1, right? Type 1 Dirac system. You can go and look at the topology of the type 2, like these antennas, or one loop. And then, of course, this constraint is diluted. So you can have different scales. And actually, in one of the models, we found out that you have also the same kind of stability we have in in the previous U1 B minus L, you also have here with the page width. Since this is what you want, you can break it to a subgroup, etc., etc. But this is very important. In this particular model, which is, in my opinion, is the easiest thing, and also very nice, in my opinion, of course. The constraints are very, very nice. Dangerous, but nice.
Okay, so let's see if there are very last questions from YouTube. So I don't know if in the audience there are more questions. Otherwise, okay, let's thank to Eduardo for such a nice webinar. For all the people that follow, for all the people that is following us in YouTube, you can either to subscribe and follow our social network to see when is the next webinar. Let me just remind you that in 2 weeks more, February 17th, is going to be a webinar from Itziar Arechaga. So to stay tuned to the announcement and everything. So now from this time, see you in a future in this Latin American webinar of physics. See you to all.
Gracias, gracias. O sea, luego invitan a los experimentales.